Sound check. Seems okay. This is our first course meeting for Stats 385 Fall 2019. The course is Analyses of Deep Learning. It's very similar in concept and spirit to a course that we offered in 2017 called Theories of Deep Learning. The change in title is emphatic, and we'll get to that later. There are some posters that are out there around campus that you might have seen that show speakers in hazmat suits, and then Vardhan Papayan and myself in a tank. I guess this has to do with the TV series or Netflix series called Chernobyl. And I didn't understand that there was any possible interest of anybody in the Ukraine until this week. Suddenly it's highly relevant. Vardhan, how did you know?
I guess.
Okay, anyway, it's super relevant these days. And Yixiao Zhang, who also goes by Joe, is a little bit down there. And he joined onto this project a little more recently. Vardhan and I, along with Hatef Monajemi, a postdoc who moved on to industry, gave the earlier iteration of this course. So some details. We'll be meeting on Wednesdays at this time. I don't think that the room number there is right, by the way, but at the moment we're in this room. There's a possibility that we're going to move to 370-370, and we'll do a course announcement through Canvas if that happens. And it says September 27th. I think today's actually the 25th. So there's a variety of small changes that need to be made on this. Anyway, these slides and other materials will be posted at our website, which is in the outside world, visible at stats385.github.io. There were, as I've said earlier, slides and an earlier iteration of this course, also videos from those, which will be relevant at some point. We're trying to not overlap too much with the talks from previously, so you ought to be able to get some benefit from all the earlier slides. If you go to that GitHub site, you will see this splash page welcoming you, and it will give an idea what we look like, but we're all right here, Vardhan, Yixiao, and myself, and we're very happy to meet with you. You may have seen the slide, rather fanciful Ukrainian idea of what we're trying to accomplish here. Thank you, Vardhan, for the inspiration. This is the bridge of death at Chernobyl.
Yes.
And these are first responders in hazmat suits who are destined to die of cancer. This gives you the feeling of Ukrainian humor, I think. Okay. Anyway, the way that this is organized, we have weekly speakers, and there are a variety of luminaries who've made a number of important contributions to the field. And so instead of any of us acting as authorities in this, we thought we'd bring in the authorities, and quite a few of them have responded. So I think we have a nice slice of both theoretical and empirical insights into deep learning at the current state of the art. One thing is that if one speaker were telling you about the current state of the art, it would probably be very up to date on their particular interests, and then probably years out of date on everything else. So this way we get people who are more up to date. On the other hand, there might be issues with a unified viewpoint and notation. We'll try to fix that if any discrepancies arise. So before I get into details and very specific items, I just want to say something of a general nature. In the 2017 iteration of this experience, Theories of Deep Learning, I gave a lecture and a half at the beginning about the significance of deep learning and why it's important that people on university campuses pay attention to it. So I'll just rehearse for you some of the bullet points, but the slides actually have tons of eye candy and data graphics and so on that make these points much, much better, but they take more than an hour to go through. Unfortunately, we just don't have that time at the moment. The first point is that there's an unprecedented success of deep nets for machine learning tasks in vision and more recently in natural language processing. And that could be attributable to a variety of things. Could be attributable to the idea that deep nets are somehow uniquely suited to these tasks. Could also be attributable to the idea that certain large industry players have made unprecedented investments in making this technology the method by which one should approach those tasks. Now, we'll never know actually which of those two things is true because we'll never be able to make a comparable investment in other technologies. Sort of what's done is done. Eric Schmidt in 2012 wrote a massive check, bet a huge amount of money continuously on this technology, and so we just see the aftermath of that. At the same time, there's been tremendous media attention on deep nets, and again, there could be corporate entities with PR teams and so on investing massive sums in order to make us all think that this is important. There are people working round the clock to promulgate the story of deep net's importance and so on and so forth. That could be a reason that we're here as well. I don't have broken out for you the public relations expenditures associated with entities like Google and Facebook, but definitely they do what they can to keep their shareholders believing that they have a unique and important technology. As I've said, there have been dramatic investments in deep net technology, and this is something that's more directly relevant for the careerists among you. So, roughly speaking, Google hired about 1,500 researchers between 2013 and 2018. I believe that this has taken a pause, so it might be less relevant for the younger of you. But during that period, they hired well over 1,000 researchers that they assigned to do some variant of training deep nets and working on certain problems that are, important to Google, and maybe gave the researchers also some time to do other things. This is a gigantic investment. It's like the kind of investment you would make in wartime if you had a killer weapon that was going to destroy the other side. To understand just how big this is, if we look at all the cumulated hiring in computer science in North America, net, like where we stand right now, maybe there are 1,500 CS faculty in North America. So basically, an investment was made that was equivalent to the size of the existing CS profession among researchers. And so they've created their own alternate profession. They've created their own alternate view of what's important. It's all under the control of one person who's, the CEO. And all of those people can be directed to work on specific things. So it's much more unified and much more powerful to unify when you have it under that control. So that is a pretty dramatic investment. Another issue is that despite all of this investment and despite the enthusiasm and despite the media and despite the success, this is something that's purely an empirical matter. That is, there isn't some master equation that we derive this from according to accepted principles that we might have been taught in some course in physics or traditional theoretical computer science or mathematics or statistics, double E, any of those fields. So by the standards of those fields, we really don't understand anything, because in those fields, we would like to be able to derive something that we make massive investments out of some principle that we really understand very, very clearly. As you'll see, there's many moving parts associated with deep nets. There's a coalescence of a group of experts around what to call those moving parts and how to deploy them. But it wasn't like there was a set of equations and you just had to put many people out there to kind of implement those equations. There was instead more like a bunch of fussing around in people's garages, and they found different ingredients that seemed to provide a successful way forward step by step. Now, it's perceived that there are massive stakes in this. So if we just take some of the implications of the technology, one could be that we may have self-driving cars sometime soon. And in order to realize that vision, we need computer vision, and we need it at amazing levels of accuracy. Humans are able to drive cars at a rate where they have adverse events, 1 in a billion minutes, or perhaps it's 1 in a higher number of minutes, but that's a very demanding standard of accuracy. And there's just no way at the moment that you can empirically determine whether a given system has a failure rate at that level. So if you're putting this out in practice, you're saying that we cannot prove that we're able to reach human levels, but we're going to, put hundreds of billions of dollars of capital investment, which includes people's lifetime savings and various, retirement obligations and so on and so forth. And we're betting it that this is going to be successful. Okay, so this is something that at least gives pause, the scale of the investment that's being made against the scale of the lack of theoretical insight as why this should even be possible. So we would like to be able to analyze these systems and understand them better, and that's why we're here. That's why we have something called Analyses of Deep Learning. Are there any questions, objections? Anyone care to, take me to task for anything that I've said on this slide? Okay, so what I'd like to do for the rest of the time, so by the way, I'll just call your attention again that we have slides about the social significance of this. I just mentioned self-driving cars, but obviously many, many things are impacted by the successes that we've been seeing. And in particular, there's all sorts of tasks that you used to have people do that it seems we're on the threshold of being able to outsource to computers. And that will have massive implications for the employment landscape and for how people spend their time and so on and so forth. So we're going to be making rather large investments in changing how people spend their days and how they earn their livelihoods and so on. So the technology is really transformative if it goes that far. And then, lots of people are making bets of various kinds about how far it's going to go. So you may want to look at the lecture 1 and 2 slides from the 2017 iteration. Again, if you go to the 2019 iteration GitHub slides, there's a link there to the 2017 ones, which includes video links. Okay, let's just review some standard notations, which we hope many of the speakers will live with. And then there are a number of statisticians here. So in an effort to engage them, because they may be the people here who have less knowledge about this topic than people from other fields, there's a little bit of a bow in their direction to remind them of how this connects with things they might know. I'm in a stats department. I have a stats background, and so I'm tainted by that, you might think. In any event, we'll try to be fairly orthodox. Okay, standard linear regression is a workhorse of everything to do with using data to make predictions. So I think everybody knows the basic slogan that if you're an entrepreneur and if you're raising money, you're doing AI. If you're hiring, you're doing ML. If you're actually doing the work, you're doing linear regression. There are people who dispute that, and they would change the last sentence to, if you're actually doing the work, you're doing logistic regression. So basically, these are, okay, in linear regression, you have a response variable yi, and then you have some predictor variables xi. I index the different examples that you have, and there's supposed to be a parameter vector beta that maps you from the predictors into the predicand. And in logistic regression, it's similar, except that we're going to score how we do things differently. In linear regression, we score by how different the predictor, the final prediction, beta transpose xi, is from the predictee yi, according to squared error or Euclidean error. And if it's a vector response, then we'll use, a Euclidean norm squared. In logistic regression, we have a loss function that we could call rho, and we're taking the response variable in simple logistic regression just to be plus or minus 1. And then we take the prediction to again be beta transpose xi, but we essentially flip the sign depending on what we're trying to predict, either an example or a non-example. And then rho of t is a very simple function of t, sometimes called the logistic loss. So logistic would be there's a binary response. Multinomial logistic would be that we have a categorical response. When you look at a lot of machine learning tasks that are associated with image understanding, they could have categorical responses like label this a cat, a dog, a cow, a car, etc. So you have different category labels, so we'll index categories by C. You would have the same basic structure, beta transpose X, except things that were vectorial before become matricial. And so the output of the output prediction is latently, instead of a scalar, now a vector, which is a vector in the dimension of categories, number of categories. And then the rho function that you deal with is the cross entropy, which is written conveniently as indicated in the display second from the bottom. In general, in any of these tasks, you formed a loss, which is of one of these forms. You have a prediction, and you're trying to find the parameter vector beta or the parameter matrix beta matricial that's going to optimize that. Any questions or problems? So this is very orthodox, and I think everybody who's taken a stats course or machine learning course has probably seen it in just this way. Many people who do deep learning don't really need to know any of that stuff that I just had on the previous slide. What they really need to know is, give me a stanza of code and show me where I can hack it. I just need to know, like, what is the part of the stanza that never changes, and what is the part of the stanza that I can touch? And that's all I really want or need. So here would be the business end of a stanza, and there are some things here that you could touch. In this particular example, the data are being set up as an artificial synthetic data set. So we've abstracted out the task of loading in the data by just making fake data. And that's indicated in the second stanza there that you see. And then linear regression is performed on this by just invoking PyTorch in the appropriate way, as indicated here. From the point of view of show me the stanza and show me what I can change, you would not always want to be using synthetic data. That would really call you out as a pure theorist, first of all. So that middle stanza you would want to change to somehow get your real data in there. And you wouldn't want to be using linear regression because probably if it could be solved using linear regression, somebody did it years ago. It's always worth trying, but presumably you're dealing with something that needs a better approach. On the other hand, the general approach that's indicated here teaches you how PyTorch works, and so you can understand that by dealing with things simply through appropriate overrides to the code stanzas that you see, you can accomplish some fitting procedure. Now, under the hood, what PyTorch is using is not really up to the standards of traditional statisticians, traditional computational math, computational science people. Because if they were trying to use linear regression, they would use high quality linear algebra packages that have all kinds of guarantees and extremely well understood properties in such a way that using those packages you can get answers that are accurate in some cases, basically up to machine precision. Instead, what you're getting with PyTorch is an extremely loose fitting process that would have been shocking and repulsive to anybody over the age of 40. Like, just basically for this, I went to university. Roughly speaking, it's got maybe one ingredient that was not obvious to Isaac Newton. And that is that if you just take random chunks of the data and do a very, very approximate gradient descent, you can get something useful on some examples sometime. Like, Newton would have been embarrassed. And anybody over the age of 40 would have been really embarrassed. It's like just crazy that this is where we are. We've thrown away 200 years of intellectual development like that. Okay. Anyway, this is where we are, is that this technology relies on a very simple idea, which we're going to take a random batch of data that is somehow, small compared to all the data we're ever going to look at. We're going to compute the gradient explicitly, and then we evaluate it, and then we just go downhill according to the gradient with some very, very simple prescription for going downhill that might even just be as simple as type in a number like 0.001. So, okay. And then we're just going to do that again and again. And of course, we have knobs that we can play with. There's batch size. Can we change that 0.001 to some other number? Maybe we can evolve it as we go through the subsequent epochs of applying this simple process. Maybe have a scheduler to make it sound fancier. And we can say, okay, we don't want to throw away everything that's been done in the last few hundred years. Maybe there are some things that were done in the linear algebra and scientific computing that might help us just a little bit. So we might put some adjustments on this algorithm so that the norm of beta is controlled, because maybe we've heard that helps. So that's called the method of regularization, Tikhonov regularization, ridge regression. It's been used by Bayesian statisticians for, centuries, stuff like that. Maybe we don't want to throw that one away. And then another thing is that this is a very slow way to proceed. So conceivably, there's a tendency for successive gradients to be almost the same. And so we might just speed up the process a little bit by saying, well, we know that successive gradients tend to be the same, and if you're getting a really different answer right now, it's probably because the randomness in your choice of batch or something. So we'll make some adjustments there. And then we might have a very sophisticated, cool thing where we change eta maybe as a matrix in response to things that different coordinates are doing. There are algorithms, variations out there like eta grad and atom, some of which are pretty standard at this point. But at the core engine there inside of a system like PyTorch is we can just do this. We can just go downhill and we'll get somewhere. And if you said this to someone 15 years ago, they would say, there's just no way that you can devote all the intellectual output, years and years of PhD graduates from the pinnacle of a civilization are going to be devoted on such flimsy principles. But we have done it. It has happened. Oh, by the way, before I move on, are there any objections, anything here that... Okay. And I come before you in all humility, right? I mean, it's essentially everything I've learned is wrong, according to this. So, far be it from me to tell you that this isn't happening or it's not right or something like that. I'm telling you, it's just very in need of explanation. So here's a learning rate scheduler, a stanza of code with, there's in red some adjustable buttons that you could imagine changing. And you can see there that in the optimization, there's some specification of momentum and weight decay, and there's some specification associated with the batch size and so on. The key thing that PyTorch really contributed, and before that TensorFlow and other systems, was a really slick thing that I think, that really a lot of credit has to be given for, which is the reason that this is a coherent technology is that literally you just specify these very, very basic things. There's very little code that has to be input in order to get a system like this to work. The key thing is there's an automatic differentiation that's done extremely well and which is extremely effective at making this a coherent package so that it's very easy to modify the objective and you'll still be doing stochastic gradient descent on the objective. Whereas if you had asked, many mathematical scientists to do this, they would probably be very careful about doing a one-at-a-time optimizer where they understand, logistic regression and in a dedicated way, they understood very, very clearly all the properties of the gradient and the Hessian and so on in closed form. This essentially renders all of that not needed. And so it allows lots and lots of people who don't want to be doing differentiation and by hand operations to get into it. And so there's a lot of popularity of it, and it creates like a whole new view of what you must be doing in order to move things ahead using this base technology. Any comments? Jordan, Yixiang? So here's an example of the training loss that's achieved on I suppose this is linear regression, and there's certain moments at which you see markings and you see that the learning rate is adjusted as we go along with something that's typed in to something else that's just typed in. And we're doing many thousands of iterations, in this case 7,000, and there are some different adjustments of the learning rate, and the training loss drops fairly abruptly as the learning rate is modified. So experiences like this that we see with linear regression are typical in many other cases. At the moment, there isn't some very clear prescription that automatically knows what learning rate to do. And what's typically done is use the advent of the cloud to just fire off many instances with many different learning rates and just see which ones seem to give you the best results. And then you just select one of those many different runs. So on top of just using a gradient method, we're also just using brute force along with that gradient method. We don't even know really what step size to use on these things. And that's considered a feature as well. Like we just so by the way, this is a technology that's promulgated, for example, by Google. Google is a cloud provider. Cloud provision is a massive generator of unprecedented wealth. So I just read recently that total cloud services among the big three, which would include Microsoft Azure, Google Cloud, and AWS, is at well over $50 billion a year at this point. The margins on that are, probably 50% or better. Now, the Stanford endowment, which is based on the loyal and very beneficent contributions of, hundreds of thousands of alumni over more than a century, including an initial bequest that was based on an epic defining achievement of linking the two coasts using railroads. All of that adds up to about the same amount of wealth, 25 billion, as 1 year of cloud credits at the moment. So this is like the amount of wealth being generated by this, which is paid in by companies and individuals and so on to these entities, is comparable to creating one new Stanford every year. It's, I think Stanford is, one of the premier achievements of human civilization. And this is a lot of wealth represented here, and it's like 1 year of cloud activity netted out with profits visible. Okay, so that's a lot of money, and I mean, if I were trying to popularize a technology where I get paid for inefficiency and just having to do lots of stuff, I would have a conflict of interest, right? I mean, you would understand that. Okay, well, to make the step from linear regression, where admittedly we know kind of closed form expressions and we can do everything through modern linear algebra packages and so on, to fully connected neural network is just kind of a single step within this approach. Basically, you just make a few key changes to some stanzas of code and you're up and running, and you've made the transition. So in regression, the prediction that we had a scalar output, beta transpose X. In a fully connected feed-forward neural network, say, the prediction is going to be written using a series of new entities, which I will discuss as they're fairly standard, but we can still think of it as the equivalent of f of xi semicolon beta. However, beta is matricial and has, could have hundreds of millions of parameters in it, and xi is vectorial, but it could result from vectorizing some high-dimensional vector. And f is also going to be vectorial in output. Okay, so the way this is written here, this is one example of something. There are, many, many deep net architectures out there, and different corporate entities have their own favorite, and you may find, that you like one or another, or that it's more convenient to access one or another. They all have a sort of some general flavor in common. So here's one example of such. We've got a chaining together of some matrix multiplies combined with some simple scalar nonlinearities applied coordinate-wise. And I'll explain this in more detail. But the key point is that the class prediction that you're going to have here is a cascade of a series of very simple things. Questions, problems? Please.
Associating to your previous slide, I was wondering how long it would take for Google to do as much research as Stanford has, because they aren't quite as much as we do every year.
So the question is, how long would it take Google to do as much research as Stanford has? I'm not sure that's a fully scoped question, but are you saying like how? So Google research of the visible kind tends to be 4-page papers, and Stanford research is much more varied. So an example of Stanford research is work by René Girard, who was a professor of, I guess, French literature here. You can read his life story. But for example, he was admitted to the French Academy's Immortelle, and his basic idea was that all of modern society doesn't matter so much. We're just pretty much all built the same way. We're kind of very basic. We need a very primitive leader who is brutal and is like maybe a kind of tribal chieftain. We all envy each other, and when we see someone who's out there who seems to be getting more bennies from the tribal chieftain, we see what they're doing and we copy them. And this is called it's a mimesis hypothesis. It would take millennia for Google to ever come up with this. And I just don't see anyone from Google being admitted to the French pantheon of the Immortelle. On the other hand, if you're talking about writing 4-page papers on the latest parameter tweaks in deep learning, well, so they have TPUs. Instead of PyTorch, they have TensorFlow. They have, vast computational resources which don't require their researchers to pay them, I think. I don't know their internal arrangements. Okay, so they can be very productive. So in the most recent iterations of NeurIPS, there are significant fraction of all the submissions are coming from people at Google. I don't have the fraction to tell you right now. It might be a fifth, it might be higher. Okay, so they're doing a big fraction of all the research in empirical deep learning, no question. Did I answer your question?
In part, I think when you said the question was not fully scoped out, you pointed to, Stanford having departments that were created out of, railroad emissions and other important contributions. But Google tomorrow could be more than a software company, right? They could delve into literature. I don't know how, but...
Well, I don't want to minimize their contributions. They did scan a big fraction of all the world's books, and they made them available through Google Ngram Viewer. I think that's pretty meritorious. They've done many good things. You're saying, could they compete with universities at what universities do? Probably not. They're not in that line of work. This is a university with a hospital, medical school, many Olympic gold medals. It'll be a long time before there's a gold medal to somebody at Google. It's just apples and oranges if ever there was. But definitely they have more full-time salaried staff doing deep learning hacks and tweaks. Are there any other questions or statements? Please.
So the W's are linear operators, and so it doesn't have to be just 3.
Oh yeah, I'm going to get to that. I'm just giving you, this is just one example,
okay.
And I'm going to say more. This is just to contrast the two. So here, the main point is, like, we're going to, for statisticians who might be losing the thread, we have beta, right? But we're going to give up. There's not going to be any beta in general. There's going to be this other stuff, and then it's like beta is going to stand for a whole bunch of matrices and other stuff that's all glommed in there. Okay, so let's get to what has become the standard terminology. And I'm told that this list agrees pretty well with the book on deep learning by Goodfellow et al. And so you might want to look at that book, or at least know this terminology, because that book became kind of canonical in this area. So there's a collection of matrices with what are called weights in them. There's a collection of vectors, which are called biases, although they can sometimes appear as just like an extra column or row in a matrix. There are features, H, which capture the output of some stage somewhere. And then there's pre-activations, which capture the input of some stage somewhere. There's masks, which are diagonal linear operators that are associated with the derivatives of the nonlinearities at some stage. There's, if we're doing multinomial logistic regression or doing cross-entropy optimization, there are logits, which are familiar to statisticians. There's a loss, now written in terms of theta rather than beta. There are, in the computation of the gradients, we need, first of all, the backpropagated errors. We need a notation for that. And then there are the gradients themselves. So, for example, we could take one of our data examples, input it to a matrix operation, and then shift it by a vector. Then input it into a nonlinearity, which we displayed on the previous slide, called ReLU, which is just the positive part. Nonlinearity, then output that, and then repeat that type of operation in a cascade. Here we're only showing 3 stages, and I want to think the question that we had. There could be many stages, and there can be other architectures, but we're just working up step by step to give you the standard ideas. Then at the end of the cascade, there might be a logit operation and then some accumulation across the examples that compares the response variable or label with whatever came out at the top of the network according to some loss measure. So as I said here, the features capture what's going on somewhere along the way. In between the ReLU and the next layer of the matrix, so that those are called features, because at the very top layer, before going into the logits, the features are in some sense the at the very top layer, what you're seeing is a multinomial logistic regression if we have categories. And so it's effectively like there are some features coming in and then you're doing logistic regression. So that would be, in this particular case, that would be like right up here somewhere. So that terminology originates there. The pre-activations are before the ReLU, and so that's a way to understand essentially what's being presented to the ReLU. The masks are the derivative of the ReLUs. ReLUs as we saw on the previous slide, are just the positive part. So if you're above 0 on input, the derivative is going to be 1, otherwise 0. So we get that the mask is indicating whether you're above threshold or not. You don't always have ReLUs. It's not every corporate entity wants you to use ReLUs. Sometimes you use other kinds of nonlinearities, and then D would be more general than just having zeros or ones. You would have some other results there. And then there's the logit operation associated with the cross entropy or with other loss measures that you're using. So after you've applied that, then your loss measure is going to look at what came out at the top of this cascade and compare it in some way with what you're doing. Now, in order for PyTorch to optimize this thing for you, it follows a backpropagation algorithm, which has been known for 30 plus years in the machine learning community. For example, due to work of people like Jan LeCun and Jeff Hinton and others. I'm in no position to attribute originality, but it's the chain rule of calculus, so it has a heritage that goes back quite before that. And so it's a very simple idea that we're trying to go downhill according to this cascade of things. So the derivative of the loss with respect to what the parameters are, which in this case would be things like the W's and the B's, is something that involves using the chain rule in a structured way. And so there's an elegant set of relationships that are, this is just eye candy illustrating the backprop rules, but I think you could work out for yourself quite a bit of this. And it's more a matter of just learning the terminology that people use, how they like to write these rules down. And then finally, the gradients can be written in terms of these components very explicitly using the activations and the so-called backpropagated errors. So if you remember what we had to do with linear regression, there was some stanza at the bottom of the display when I presented that where you had to define initialization and a forward map. And the business end in defining something analogous of this much more complex nature is simply the following stanza. So you are going to have defined in this way a cascade of operations by a very simple sequence and then return it. So of course it would be more complicated if you had more layers, but it's not conceptually more complicated, it's just simply more elaborated, but along the same principles. So the key thing about this is that there's like one pattern for all. Once you learn what these stanzas look like, you learn how to change them, and you can, essentially mimic what other people are doing very effectively just through your own devices. If we had, for example, 17 layers rather than just 3, well, then the stanza would be longer. It would be, in the 30s of lines rather than here where we have about a dozen lines. But it's not in any way obscure what's going on. Questions or problems? So conceivably in this plot, I should know what this says. It's got the exact same title. I think what it means is we consider an example where the response is like what we had in the linear regression model, and the prediction goes according to everything that we've just set up for scalar response rather than categorical response. And then we ask PyTorch to optimize, and it has essentially the same behavior as what we've seen previously in terms of learning rate, but now the training loss that is experienced scales somewhat differently when you use this. Vardhan Yixiao, did I mangle it in some way? It's okay? Would you correct me if I did mangle it?
No.
I hope you'll correct me if I mangle something, but possibly he's saying that because I've already mangled so many things. Historically, we should say, so Jan LeCun, who was the co-winner of this year's Turing Prize, one contribution that he definitely made was to developing a successful neural net for zip code recognition that, in my understanding, eventually led to, the U.S. Postal Service actually using that technology to deal with like all the mail that's out there. So probably mail is less important than it used to be, but let's say 25 or 30 years ago, used to have episodes of mail sorters going crazy and taking, assault rifles and shooting people because they just couldn't stand doing that kind of work. And you haven't heard about that recently. Partly, there are many horrible massacres taking place, but there used to be this concept of going postal and so on and so forth. So possibly we have less of that because there's less mail with handwriting. Possibly we also have less of that because humans don't do that task or are not such crucial cogs in the processing of billions of pieces of mail. So seems like a good thing, I think. In any event, it was not just demoed, but led to successes. Key elements there, which we haven't spoken about, that the W matrices that were involved were not completely arbitrary. So I might have given you the idea from the previous slides that W matrices were just anything. In modern nets, what you typically have is that in the first several layers, which could continue for some time, these are based on a very special structure known as convolutional layers. And then eventually you make a transition where you have fully connected layers, so dense matrices, and then the matrices can have just the full matricial structure you would expect. But at the lower levels, you don't have that matricial structure. So there's this hybrid of some layers of CNN and then some layers beyond that. So the upper layers are called pooling layers, and the lower layers are called convolutional layers. And this eye candy that came out of this initial network effort in some way pioneered that structure. And here you see someone looking at a late 80s era terminal showing that they can somehow recognize handwriting. I'm not sure that this attribution is actually correct. I believe that Fei-Fei Li was the Stanford professor involved as a team head in a team that created ImageNet, and I'm sorry that I don't personally know everybody who should get credit here, but definitely she was part of it. I just don't know all the actors, and I can't be the person to attribute credit and blame. Key point in the emergence of the deep learning technology that we know is a contest which is based on this data set. That contest set up about 1 million images with labels from about 1,000 classes that had been collected from data, I think, gathered, kind of wherever you could on the internet. And for at least the 1,000 classes that I mentioned were the ones that were used in the ILS VRC competitions. Those competitions then over time led to evolution in technology, and at some point there was a big improvement due to the use of deep learning, which led to a lot of what we're talking about. A network which became famous from this is AlexNet, which started the use of ReLU and had very particular parameters like batch size 128 and SGD momentum 0.9, which you've seen earlier in the code bodies that we showed earlier in the lecture. And then learning rate, which is typed in at 0.001, and then was adjusted manually. And then some weight decay parameter also just typed in arbitrarily. The key thing about it is that the images were 224 by 224, and little image patches of size 11 by 11 were taken out and input as what could be operated on by the W matrices. There's a width dimension here that is implicitly part of the whole story, so that you have different channels being generated from what's essentially a single channel problem. And so this, for some people it might be easier to think instead of matrices as higher dimensional entities, arrays with multiple subscripts that are carrying different channel information. And in some fields they call that tensors. And then in some parts of the mathematical sciences, there's objections to using that terminology because just an ordinary array is not enough to make you a tensor, but who cares? We're stuck with this terminology. Anyway, it's a high-dimensional array, and so there were all sorts of hand-designed things around this, including the progression of the number of channels with depth and the progression of the spatial dimension. So the original image is spatially patterned, and the initial convolutional nets preserve that spatial structure because it's inherent in the way convolutions work. So for a few levels, you're going to have spatial structure, and then things go abstract as you get out to the dense layers, and then that's input. So this kind of architecture by itself was not completely new. The use of ReLUs, or positive part operations in between, was somewhat novel. At the end of the day, with all of this happening, you ended up with just 1,000 dimensional output, and that matches the number of classes in the ILS VRC data set. And that matches essentially what you would be doing in logistic regression or any kind of statistical class labeling. Now, getting this to work the first time shouldn't be minimized. Like this is, like the Wright brothers flying or something. So there were a lot of clever tricks that developed between 2012 when AlexNet hit the scene, and let's say 2015, and these include Dropout, also from the team that used AlexNet. You can see that as item 2. Dropout is a way to do ridge regression or weight decay by damaging your data randomly. And so basically you create fake data by taking your data and throwing away some of it, or setting parts of your data to 0. And the equivalence to doing some kind of quadratic penalization can be worked out. But it's very nicely suited for this kind of optimization paradigm. Whereas if I tried to do an equivalent regularization by, formally specifying it, say the way that Professor Boyd and others would teach you in EE, then I would need a whole different approach to optimization, say based on CVX and other things. And so this was a master stroke at how to extend this SGD formalism and add regularization, but with all the exact same code structure. It's not a new entity for mathematical scientists, but it's really a clever trick if you actually have to get some things to work. I guess that's a dropout is, I think I may have said it. Another idea that came in was the set of innovations around ResNet, which was an important development, I think, around 2014-15, where an extension to the model was made where it's possible to feed forward from an earlier layer to a later layer, and thereby reparameterize what you're doing so that the intermediate layers, instead of computing the whole prediction, are computing a differential prediction. And that, in a way, recenters the task of those intermediate layers so that if they just say 0, it's kind of okay. On the other hand, if they see the need, I'm giving, anthropomorphism here, but if they see the need for a correction of what the earlier layer would be, they just focus on the correction rather than, reproducing things. Batch normalization was another improvement that was found empirically over this period, where things were rescaled and recentered adaptively so that they would be always in standardized coordinates at each layer output. And it was found that it would be very, very tricky to initialize a deep net if you didn't do this, and you could just burn up massive amounts of computer time and research money if you didn't do this. And then after doing this or implementing it as part of your approach, you're much more likely to get results sort of straight out of the box. So this is the key point to pay attention to, is that this competition was based on the ImageNet efforts that were done here at Stanford and also with other collaborators that created a contest. In the first few iterations of the contest, the winners were not based on deep nets, but were instead based on a kind of support vector machine approach. Then in 2012, there was a big improvement, big in the sense of 10 percentage point drop in error rate. And there's a whole story about that. But then following it, there were a series of smaller but still important improvements that were made. And you can see down here, for example, ResNet, which introduced the idea of the skip connections and so on, was an ILS-VRC winner. The people who were involved in some of these different contest victories became, very highly sought after figures in the, machine learning hiring landscape, and went on to have rather important roles in various industrial research labs and so on. So this is a case of a contest really changing the world. I'd like to make a couple comments about it. So the technology that was used in the beginning was support vector machines, and then all the later ones are not support vector machines. As I said before, we don't know that support vector machines couldn't get to here. What we know is that there was a technology crossover, and all the investment went into using deep learning after this point. And we know that what's been reached is somehow the level of performance that people can do on this task. So there's no real call by anybody to invest money in trying to find another technology that will do this, because it's thought, we know how to do this now. Do we really need another technology? It's going to cost money and time, and people probably don't want to spend their time or their money just trying to catch up. So we don't know that support vector machine couldn't get here, but there are people who have been trying, but the resources and scale of what they can accomplish is very small in comparison to the massive momentum that's been gathered by all these other teams working using another technology. Another thing is that there was a kind of polarization and Cold War in machine learning that was present for 20 years before this contest victory. So for the first 10 years, let's say from the mid-'80s until late 90s, there was a lot of work on neural nets, and then there was a crossover in the late 90s towards support vector machines and similar things. And many contests and most of the technology development went into the support vector machines over time. And there was, I suspect, a fair amount of antagonism, and René Girard could be brought in to explain everything that I'm talking about here. The inherent tribalism, which is such a pathetic part of the human condition, and other things that could explain that. In any event, we had this technology crossover, and a different tribe is now in the lead. Any questions or problems? Okay, so I'm like way behind, but anyway, I'll just quickly say, so that's some terminology. Now I'll just quickly mention some phenomena that has been observed through experimental and theoretical analysis of these, and which will be exposed at length in later lectures. One of the things that's really pretty amazing is if you look at the weight matrices in the early layers of neural nets, so those are CNNs, and you can look at the sort of the footprint of those things, imputing what they do on the input images that they came from. And what you'll see is that they act as filters, which are selective orientation filters, or they're looking for particular patterns of color, or they're looking for particular high-frequency alternating textures. So there's nothing in this network that knew about textures, knew anything about the experiments in neuroscience that showed that the human visual system does exactly this. but yet they were found just from the data. And if you're interested in following up on that comment, there was a paper in Nature by Olshausen and Field in the 90s that showed that you could, through unsupervised learning on natural images, learn the optimal representation of images in some principled way, and you would get these kinds of features. In the AlexNet example, you're learning through supervised, task-oriented, and you're coming up with exactly the same things. So there's a neuroscience angle here, which is quite interesting to think about and explore. A second point, and this is one that the neuroscience would have possibly predicted, although they wouldn't have been able to be quantitative about it, is early vision in humans, is based on children seeing lots and lots of examples over a period of time. And then the visual system develops over a period of months after birth. And then whatever you've seen at that point is the basis for being able to perceive lots and lots of other things in the future that maybe you didn't see in those few months as a child. So there's some amazing transfer that goes on, that your early visual experience adds up in a way that it's going to equip your neural equipment with just the right training so you can deal with all sorts of things in the future, such as PowerPoint slides. And children don't have any experience of that, and yet we can look at them and understand. It's a fantastic miracle. So something that happens with deep learning that has been proven time and time again is I could train up a deep net on some vision task, and then if I had plenty of data and got really good results, I could use that as an asset for future studies where maybe I don't have such good data. And what I would do is I would throw away the fully connected layers at the top and just keep the convolutional layers at the bottom as my basic early vision apparatus. And I would only try to train the fully connected layers at the top. I would freeze the CNN layers. So I could learn, say, using ImageNet and then train on some completely unrelated data, like looking at, cardiac images or brain images or some other kind of image data that I'd be interested in. And so that the ability to transfer those things is a really fundamental, I would say, discovery that has deep significance for neuroscience, but it's not completely understood, and there's no theory that we can derive it from, but it's just amazing and very important. Another thing which will presumably be spoken about by one of our speakers on November 6th is that if you work adversarially, you can construct data that will confuse these networks. So pushing this to extremes, you could, show a vision system, a camera with a stop sign. You can show a vision system's camera with something that to the human eye looks like a stop sign, but it's been perturbed in such a way that it's not recognized as a stop sign. And in this particular example, you can very carefully perturb an image of a panda to produce the neural network's classification that it's not a panda. So that suggests there's a great deal of instability in what neural networks are doing, and yet we're making a massive social investment in this technology. There's a variety of other things which I should discuss, but I think we pretty much run out of time. So what I'd prefer to do is I'll send you notes on what I didn't discuss so far, and instead we'll just take questions. The slides as I would have presented them, will be posted, and the notes that I send you will be also posted, so you can get the content of the next few slides in that way. Are there any questions, comments?
I want to ask you a question from the earlier slide. So the last part, you're going to calculate the lodges. Or is that how to pronounce it? Do we still have to do cross entropy, or it can be something, a general like type of function, and what property it has to
Right,
have?
okay, yeah, thank you for the opportunity to clarify. When we're doing cross entropy, then logit is the appropriate thing to do at that stage. If you changed the objective function to be something else, so you weren't using cross entropy, then there would be, a different thing would show up there. So you just have to match the nonlinearity at that stage to what your ultimate objective is. Other questions or problems? Okay, so next week we're having Professor Stefano Soato from UCLA, who will talk about information bottlenecks and related ideas that he's been one of the pioneers in researching on. So we'll see you next week.